Hello, Butcho, and welcome. Today we're jumping into a very important topic from Unit 13, Nuclei. We're going to talk about the nuclear force. Now, I know this sounds a bit heavy, but trust me, understanding this one idea is the key to understanding all of nuclear physics. And don't worry, we'll explain it in a super simple way that's also perfectly safe for your exams. Okay, Chala, let's begin. To understand what the nuclear force is, we first have to understand the problem it solves. It's a really big puzzle, a mystery that's right there at the center of every single atom. Now, you all remember Coulomb's law, right? We studied it in electrostatics. It's very simple. Like charges repel. A positive charge will always push another positive charge away. So just think about the nucleus for a second. It's this incredibly tiny space, and it's jam-packed with protons, all positively charged. According to Coulomb's law, the repulsion between them must be huge. The nucleus should just explode. It should fly apart instantly. But it doesn't. So the big question is, why not? The fact that atoms even exist, that you and I are here, tells us that there must be something else going on. There has to be another force inside that tiny nucleus, a new, hidden force, something unbelievably powerful that's acting like the universe's strongest glue. To understand this, let's use a simple analogy. Imagine the nucleus is a very crowded room, and all the protons are people who really don't like being touched. They're always trying to push each other away. But there's a special rule in this room. There's a powerful friendship force that only switches on when people are shoulder to shoulder, really close. And this friendship is so strong, it completely overpowers their need for personal space, and it keeps everyone stuck together. And that friendship force in our story? Well, that's it. That is the strong nuclear force. It's the answer to our puzzle. It is the universe's strongest glue, holding the nucleus together against all odds. Okay, so the analogy is great for understanding, but for your exams, Beta, you need the official textbook definition. So let's see what our NCERT book has to say about it. So the NCERT text gives us the key properties. It says the nuclear force is much stronger than the Coulomb force. It also says it falls rapidly to zero if the distance is more than a few femtometers. And very importantly, it does not depend on the electric charge. This is the exact language you need to remember for your exams. So let's just break that down into simple words. Number one, it's the strongest force in the entire universe. Stronger than gravity, stronger than electromagnetism, anything. Number two, it's a short-range force. This is so important. It only works inside the nucleus, over distances we measure in femtometers. And a femtometer is tiny, unbelievably tiny. And third, it's charge independent. This means the force doesn't care if a particle is a proton or a neutron. The force between two protons is the same as between two neutrons or between a proton and a neutron. Now that we have the basic idea, let's dig a little deeper. Let's look at the specific characteristics of this force. You can think of them as the rules that this special force follows. So, just to recap for your notes. Rule number one is its immense strength. It is about 100 times stronger than the electric repulsion at that tiny distance. Rule number two, short range. Once the particles are just a little bit apart, more than a few femtometers, this force just disappears. It becomes zero. That's why we don't feel it in our everyday lives. And rule number three, charge independence. Like we said, it treats protons and neutrons as equals. And have a look at this graph. This shows a really special property. It plots the potential energy against the distance between two nucleons. Look closely. At a distance of about 0.8 femtometers, the energy is at its lowest point. This is the sweet spot. This is where the force is strongly attractive, pulling them together. But now, see what happens if you try to push them even closer than that? The energy shoots up. This means the force suddenly becomes strongly repulsive. It's amazing, huh? It pulls them together, but it also stops them from crashing into each other. It prevents the nucleus from collapsing in on itself. Okay, Butcho, I need your full attention now. This section is very important. We're going to talk about common exam traps, the simple mistakes that many students make and lose marks. Let's make sure that doesn't happen to you. First common mistake. Students think the nuclear force is just some special type of electric or gravitational force. No, Beta, absolutely not. It is a fundamental force of nature, completely separate from the others. The second big trap is confusing binding energy. Listen carefully. Binding energy is not a force. It's not pushing anything. It is the energy that holds the nucleons together. You can think of it as the strength of the glue. More binding energy just means the glue is stronger and the nucleus is more stable. That's it. All right, we're almost at the end. Let's bring everything together. These are the most important points from today's class. This slide is your final revision summary. So to summarize, what is the nuclear force? 1. It's the strongest force in nature, and its job is to hold the nucleus together. 2. It's a very short-range force. It only works inside the nucleus. 3. It is charge independent, treating protons and neutrons the same. And 4. Its main purpose is to overpower the electric repulsion between protons to keep the nucleus stable. If you remember these 4 points, you are perfectly prepared for any question on this topic. So we have solved our puzzle today. We know what holds a stable nucleus together. But this leaves us with a new, very interesting question to think about. What happens when this super strong force is just not strong enough? What happens when a nucleus is unstable? Well, that is the topic for our next class, radioactivity. See you then.